on this computer.
So welcome to another wonderful PL seminar talk. And today we're very fortunate to have Mike Carbin from MIT telling us about engineering approximate computation. So Mike is has done his PhD at MIT as well, and then he went on I guess a pre-tenure sabbatical / vacation at Microsoft Research, and he has been doing a lot of interesting work on figuring out how to make computers faster without having to necessarily keep the soundness of the programs he's trying to run. Looking forward to hearing your talk, and hand it to you, Mike.
Sure. All right. Everyone can hear me okay?
Yeah.
All right. So yeah, so today, my talk is going to be about engineering approximate computations. And so this is not going to be, as technical a talk as I could give, about certainly some of the programming semantics work that we've been doing. And instead, it's more of perhaps a position talk, right, of talking about some of the work that we've been doing in approximate computing, and also relating that to the work that we've been doing in machine learning community. So recently I've had quite a number of papers that have coming out in the machine learning community. People also always look at me and say, I guess you're just doing machine learning now. And I always have to say, well, no, I think I'm still doing programming language work, or just thinking about systems and programming a little bit differently. And so with that, I'll get on to, I'd say, another variant of how you might think about this talk, which is that as, clicker's not working. That as systems that learn. And so that's really what I mean is this recent emergence of things like machine learning, which we always think of as being this other space and other domain, often computer vision and natural language processing. But instead, when you start to take these types of systems apart and even apply them in our own domains inside of programming languages, such as compilers, you start to see that these look like systems. And I'd say very much approximate systems. And a lot of the work that we've done in thinking about reasoning, is on that path of research challenges we'd like to address. So with that, approximate computation. So approximate computing has been around in the systems community and programming language community for some time, but I always like to explain it again and explain it afresh based on how I think about the world. And the way I really like to explain this these days is by looking at our traditional computing stack. Let's say, this cartoon that I have, our computing stack. We have everything from applications coming on down to hardware. And the way that I got to this, thinking about this presentation, was I was actually teaching a class on computer systems engineering a few years ago. And we were going through these layers of the stack, talking about your trusted computing base, where you expected errors to be in your application, or where you might be able to trust, the results of computations. Right? And, students were going down saying, sure, applications in library are buggy. They say, I write applications, there are bugs in my code all the time, right? They'd say, we talk about compilers and runtime systems. So students, coming into the discipline aren't necessarily so familiar with those bugs, but certainly here, this audience, we understand the bugs that happen there. Operating systems. So certainly there are bugs in operating systems. We've all used Windows at some point, right? So we've seen that. And then we got down to hardware systems, right? And so the students, they sat there and we said, like, do you trust your hardware, right? And this was well before Spectre and Meltdown and all those types of issues. And they said, sure, when I run 2 + 2 on my processor, it's going to give me 4. It's going to give me the correct answer. And at that point, I had to say, well, no, actually, no. There are bugs in hardware, which was very surprising to them. And the types of bugs that I really want to talk about are, instead of these, let's say, security issues, side channels, but actually talking about real functional correctness bugs. Right? And so you can actually go right now and pull down off of Intel's website, a list of all the problems that you have in the processor sitting in your machine. Right? And so some of these are relatively benign, right? But some of these are actually quite critical issues. And so, for example, this one I have here at the bottom, its description says that it can cause a processor to hang, right, and potentially cause unpredictable system behavior. And what that actually means, it means it can produce arbitrarily incorrect results. Right? And there are many ways that this can happen, but it does actually happen in practice. And so if you are a consumer, for example, or a prosumer, you might see this when you're stress testing machines, as evidence in the style of article and quote, Or, people who really care about this are these large institutions that are running large distributed computations, where in any given run of a large distributed computation running on tens of thousands of cores and machines, it's very likely that you'll see some type of issue either in somewhere in the hardware stack. Right? It could be in the CPU, it could be down in memory. Right? So how do people cope with this problem if these problems are there and perhaps we aren't so aware of it? Well, so the one I want to talk about, the types of errors I want to talk about first are transient errors, right? And so the transient error, the idea behind a transient error is that if I run my computation once and I get an error, if I run it again, then with higher probability, I'm going to get the correct result, right? So this is going to be your concept of a transient error. And so from this perspective, you can think of classic techniques for trying to deal with this situation, where one classic one is just replication, right? Coming up with a consensus, right? And so again, the basic idea is I take my instruction or I take my computation, I'm gonna run it twice. If the results disagree, I'm just gonna run it again. And if you actually trace back into the literature to find where this type of computation, this replication first started to get into, let's say, the computational disciplines, you actually go back and find a paper by von Neumann, where you applying this type of technique to trying to get reliable organisms from these unreliable components. And if you actually look at this, these unreliable components, these were neural networks, right? Which was very interesting to see at the time, right? And it's actually related to why I do some of this work in this space, where you have this much softer general characterization of error. And sometimes these types of tolerating errors can actually be tolerated or useful in some cases, right? And in fact, right, so replication, what this gets to is instead, well, what if we just let errors happen, right? So we could replicate, but we could just let these errors happen and propagate, right? And immediately what comes to mind, if you're coming from the programming perspective, this is going to be an unmitigated disaster, right? I may have errors at any point in my computation, and things are really going to get off the rails, so I should be concerned. But instead, what I want to show you is an example of how this can actually work out in practice if you do the work and think about the impact of these errors. And so this example is here. It's the Jacobi iterative method. So this is a standard method for solving systems of linear equations. And it's not important that you understand any of this code, really, right? It's just a template. And I've highlighted the key things that you really want to understand. One is that this is an iterative algorithm. So it runs for some number of iterations until it converges, right? It has some natural convergence condition that it tests, right? And then inside it has a number of operations, right? And so what I've done is I've highlighted these operations in red to show you and illustrate what happens if you let Jacobi run, let it encounter errors, and let those errors just happen. So let's take a look. So this is an example. So here, what I've got on here is a depiction of executions of Jacobi. So the one that's blue, so this is just a standard execution of Jacobi on, let's presume, a reliable execution on reliable hardware, right? And so what we can see is, what we're plotting here is a function of the number of iterations, our distance to the correct answer for this particular problem that we're trying to solve. And you can see it has this nice, sometimes learning curve that you might see, where it essentially eventually approaches the correct solution. Right? Now this red one is actually what happens if you let errors happen inside of Jacobi and some of those operations, right? And in particular, you can see what happens. We can see initially we get this very large spike, right? We get very far removed from our actual answer. There has been some corruption, and in fact, it looks rather catastrophic. Right? It looks as though we've lost about 5,500 iterations of progress, right, in this computation, which looks dramatic. But in fact, we actually only end up adding 2.6% more iterations to this computation. Right? And so why does this work? Well, Jacobi, it's a self-stabilizing computation. Right? Once you get an error, it's as if you just started again from some random guess for what the solution of your equation is, or a solution of your system of equation is. Right? Second, is that errors do not catastrophically propagate throughout your entire computation. Right? In fact, they can be relatively local. Right? So if you go through the work of actually understanding how these errors propagate, you can think about a new technique now to actually let errors happen and get better performance, right? In fact, if you go through the literature and think about the types of overheads you'd be looking at in these types of techniques, is with option number one, where you replicate your computation, you're gonna have a 50% overhead, some clever tricks in hardware support. And option number two is 2.6% more overhead. So this could be a very productive technique, provided certainly coming from the programming language space, I'd say from the application designer space, provided that you can prove that this error is acceptable, right? And in fact, you can, right? So in some work that we had a couple years ago, we actually showed that there is essentially a logarithmic bound on the number of additional iterations that we added as a function of the amount of error you permit, right, on any given iteration of the computation, right? And so what this gave us and what this inspired us to do is, from the applications perspective, we can think about the algorithmic framework, and then that's going to map to a specific programming methodology, right? Where on the top, we had replication, and on the bottom, we have our approximation. Or what we want to be able to do is now bound this epsilon at points in our computation, such that we know that at the end, we're going to have, let's say, an acceptable degradation in performance in this particular case. So now, the way we went about that in the past and sequence of work that we've had over the years is by thinking about these types of assertions and what they mean. So if you look at this assertion again, you can see what it's doing is actually referring to two executions of the program. There's a reliable execution, so the Z angle bracket R. There's an approximate execution, which is going to execute based on this model of errors happening in the hardware. And then you're going to have this assertion that's going to bound this difference. And you can have these at arbitrary points in the program to various levels of success, depending on the techniques that you're using. Right? And so we've looked at this in a wide variety of systems, right? In our most recent system, Leto, a couple years ago that we had in Uppsala, what we did is we extended this model to be very general purpose, where we actually allowed a platform designer to be able to provide an execution model that explained how errors may manifest in the underlying execution substrate. We then had a program that would then be composed, and together it's allowed, let's say, a developer to sit down and actually verify that their computation is actually going to satisfy the invariance that they care about for the particular part form. Now, so this is one take, thinking about hardware errors. Right? And what we're doing here is, if we take a step back and think about broadly why these things work, is that many of these computations are approximate. Right? So these results are computed to a given precision or a given probability. Right? And so what we're able to do when we start to make this observation of our programs is that there's an opportunity to trade quality of results, right, for actually increased performance. Right now, certainly in the Jacobi case, we were able to actually recover. Typically, we can recover exact results because it's self-stabilizing. But in general, there are a wide variety of techniques that have played out in the community where this trade-off is not precise. Right? We're actually going to give up some performance. And so there's been a massive effort in the community not only consider errors or approximation in the hardware, but also consider this at all levels of the stack. And so this was code perforation, loop perforation, if you guys have heard of that, function substitution, taking computations and then swapping them out with approximate implementations. And those implementations could actually be neural networks, as was done in the past. Approximate hardware, as we talked about, and also relaxed definitions for synchronization. And in fact, when you start to take these all apart, is what you see is there's this broad space. There's this broad space of approximation where we can think about things like measurement error. So this has showed up in the community where I'm sensing and doing perception, and there's natural error that's coming in from my environment, and I want to figure out how to model that and how to, for example, determine if I need to do more perception, be able to successfully compute my result. Things like execution errors, as we talked about, numerical error also shows up in this context, thinking about the approximation, fundamental approximations you get by looking at floating point error. Algorithmic error if I have approximate algorithms. And then lastly, as I talked about on this last slide, but learned components. Right? And that's where we're getting to how I got in this space, right? Where we're thinking about replacing some of this computation with components that are learned from data. And I'll come back to that. But the fundamental question among all of these was, well, how do you compose exact and approximate computation? This was always the struggle when you look at any of these papers and anything in the space, and that's why we did a lot of this work on Leto as well, is that we had all these invariants that we wanted to establish about our program, right? Is internally a program actually going to be safe? Is it going to have reasonable executions after I apply these types of transformations? Externally, is it actually going to satisfy some client contract? Is it going to generalize? Right? So you can typically configure these types of approximate transformations given some data set. oftentimes are very data set specific, and this is why you have the approximation opportunity, right? And what I want to know is if my distribution of inputs changes once I deploy this system, is it going to work, right? And then all beneath this as well, we found these challenges. We'd be putting together these analyses and realizing that we need to be more precise thinking about continuous computation, real numbers, things that we hadn't quite thought about before in our community, or probabilistic computation, again, things we hadn't thought about in our community, right? And so this problem, right, so these opportunities and problems are what I've been investigating and seeing inside of this systems that learn, right? It's been a more narrowly scoped component, I'd say, of this broader umbrella, but we're seeing a lot of these same observations show up. And of course, even new observations, right? And so what I'm going to talk about today, so the rest of this talk, is one example. So an example of how we've been applying these types of learning-based techniques inside of our own domain, inside of programming languages, right? With the goal of showing you that these machine learning techniques aren't this far off of field thing that we should never think about in our community, but we've actually been engaging in tasks where perhaps learning is really the right thing to do. Right? And then I'm going to talk about some of our work thinking about the systems building challenges. So talked a bit about semantics. I'm going to talk a bit about performance. We've got these large neural networks slushing around. How do we actually improve the performance? Right? And then finally, I'm just going to leave and conclude with just some talk about correctness. And I'm happy to talk about some of the initial work that we've done there, but I'm not going to present much of it today. So all right, so that's going to be the tour. And so we're going to go through each of these things of system semantics and performance. So let me first talk about systems. How do you approach machine learning? How do you get application-specific expertise, let's say, on something, on a problem that you understand, instead of thinking about, again, vision, natural language processing, all these other spaces, right? I think, in this, when we really think about how we might make progress on verifying reasoning about these computations, I do think there is, in this direction, an opportunity to become domain experts. And the more expertise that you have on the domain, the easier it will be to articulate the appropriate specifications, and the less you'll need to rely on alternative people or alternative communities to identifying these specifications for you. And so this is something that I'd say broadly about, because programming languages already move in this direction. You're seeing this. You're seeing even work here that's going on, in MadPL, where people are looking at general purpose machine learning computations, but I do think there's some value actually looking at computations in our space. So let's talk about this system that we've been building. So the problem that we're trying to solve is a performance modeling problem, right? And so what do I mean there? What we want to do is we want to take a piece of code, in this case assembly code, and predict how long it is going to take to execute on some particular platform, like an actual specific microarchitectural revision that you have. And so this is critical. This is critical for a couple tasks. One is performance engineering. So performance engineers who are really trying to squeeze the last bit of performance out of a piece of code, they use these types of models to help them debug where they might be running into problems. Secondly, in compilation. So that back end of your compiler is using these types of performance models quite extensively, right? Is trying to make a decision, for example, with instruction scheduling. What is the optimal order for a particular set of instructions that I have? And it needs to have a model of how that decision, permuting to instructions, will affect performance. And so it uses performance models. So some function takes assembly code, in this case, and outputs a number. And the number I'm going to talk about today is throughput, right? So here, this is going to be, let's say, the number of processor cycles it takes to execute this basic block, when looped in steady state. Right? So, okay, so this is the problem. And so this is actually, it's a hard problem, right? So like I said, this is a problem that's everywhere at the lowest levels of our community, thinking about performance engineering. And it's a very hard problem because your modern processor is complicated. So this is a cartoon. I mean, it's I guess a relatively more accurate cartoon of what's going on in your modern Skylake microarchitecture, right? And so what's happening here is if you want to build a performance model, you actually need to try to model these components, right? So, the front end, the scheduler, all these different parameters that you have for every single component that you have in here. Of course, it depends on the fidelity of the prediction that you're looking for. But you really need to think about all these various, these dozens of components that you have sitting around here, right? And the unfortunate reality is that though you can write down this picture, and it's sort of a general purpose picture of how these things are generally architected. The actual specific details are very opaque. They're lost. You know, this is really the image you have of this processor. And where you get this image from is from the infamous Intel menu that's sitting around. Right? If you've had the privilege or unfortunate to have to crack through the Intel manual and go find some low-level details in here, right? But you're talking about multi-thousands of pages of specification about various parts of instructions, right? So various optimizations that might go on in the CPU or shouldn't be going on in the CPU, different parameters, instruction throughputs, latencies, all these things are in here, and there's a lot of text that looks like this, just tables and tables. You go through these tables and you start to look at the footnotes for these tables, and you actually see comments like this. And it says that all tables in this appendix are estimates. Right? Actual performance may vary from somewhat faster to significantly faster. Right? So even the documentation that you're getting is an approximation, right, of the actual reality. Right? So not only do you need to sort through this massive amount of documentation, whatever you're getting is approximate as well. And so what that means is that in practice, when you go and look at these models that are used in, let's say, LLVM and LLVM backend, instead of looking nice and detailed like this, it looks more like this, where you've got perhaps some abstraction of a decoder, scheduler, execution units, some basic parameters for instructions, and you kind of do your best effort and call it a day. Right. And so that's your modern performance model, which is going to be a very simple abstraction of a complicated reality. And so as an example, let's see if you're building this model, let's see what it takes. What does it take to actually think about how you instantiate parameters here? So here is an example. So here's the quiz. How many cycles does it take to compute 100 iterations of this instruction? Right. So this instruction, that I wouldn't expect you to immediately know what this instruction is. But we can go look in the Intel menu and find a specification for what this instruction does. And we'll see that this is actually a vector XOR that we have going on here. And so we can rewrite this instruction, do a little bit simpler. Hopefully we all understand what this instruction says. So R1 is equal to R1 XOR R1. So that's the first one. You know what our instruction now means. As well, we can now go and look at other parts of the manual and find these basic parameters that you would use to guide building your performance model, right, to be able to actually answer this question. Right, so here, these are the values that you actually go find. So you'll find that the latency of this instruction, so how long it takes to execute one instance, let's say in isolation, is going to be 1. And then the throughput of this instruction. So again, we're trying to model throughput, but this is essentially, you can think about this 1/3 as the 1 over the number of independent instances of this instruction that the processor can execute in a single cycle. So it can issue essentially 3 of these in the same cycle. Right. So, quiz just to think about. If we were in the audience, I might try to reach out and get responses. But how many cycles does it take to compute 100 iterations? All right. So let's see. Let's look at this. Let's try this thing out. So first step. So if you go and look at LLVM's model, what it's going to tell you is 100. And this seems like a reasonable thing to do, right? So if you look at this instruction, what are we going to notice? Right, we've got dependencies, right, between each instruction instance. And that's the way LLVM is going to detect us and say, there's clearly a dependence. I obviously can't start executing the next instruction until I finish executing the first one. So it's going to stack these up. It's going to look at the latency of 1 cycle per instruction, and then you get 100, right? Now, in practice, right, this isn't a reality, but this isn't the true reality. What is this instruction doing? Right, R1 XOR R1. Right, well, what it's actually doing is it's just zeroing R1, right? And in fact, you can think about it like this, right? Where I just have multiple instances of R1 equals 0. And if you go and root around in the Intel manual some more, you'll actually find out that yes, the processor implements this exact optimization. Things are called 0 idioms, and it has specific case-out logic to detect patterns of 0 idioms and then rewrite them on the fly, right, in the front end, right? And in particular, there's our instruction there, right? And also it's going to tell us that these have no execution latency. These can be actually removed in the front end, and everything's actually going to be just fine, right? So this optimized one, now we can start to think with this optimization in hand. Okay, no execution latency. I can do 3 in a cycle. This should be 33. Right? Should be good. Basically 33 on average. That seems reasonable. Now, if you actually sit down and you go measure this, or if you actually go look at Intel's proprietary closed source performance model, which is doing complicated discrete event simulations, what you get is 25. Right? And you say, well, what happened? Well, you actually have to go look at another particular part of the process and realize that this is actually going to be bottlenecked instead by the front end, meaning that it can actually issue 4 instructions at a time. Right? So now the actual semantics here that we're observing has really no relation to the specification that we're being given by Intel, right? Outside of, unless we go through the multiple steps of looking at the data, looking at the optimizations, and also looking at globally other parameters, right, of the design, right? So this is hard. This is hard. People, spend so much time trying to tune and think about these simulators, these performance models that they have in the back end. And it ends up being this methodology where what you do is you have your simplified simulator, you have your more complicated reality, right, which you're going to run data on. What you're going to do is you're going to get a data set. You're going to pass it through your simulator. You're going to measure it here down below, actually run it on your chip, and get 2 results. You're going to take the difference, and then you're going to try to say, well, what might be going on here? Why is my prediction incorrect? Why is my model incorrect? And then you're just going to refine, right? So if you look at this loop, this is now a standard machine learning loop, actually, right? So your compiler engineer is sitting there basically doing manual gradient descent for some definition, right? They're sitting there getting data sets, looking at how these things actually don't work well, finding particular blocks to try to update their predictions on and readjust their model. So what we've done in Ithemal, in the system I've talked about, is what we've done is, well, we said, well, why don't we just replace this thing? Instead of working with our manually provided performance model, the simulator writing, let's just go ahead and replace it with a neural network. Right? So that was the first hypothesis. And this was great. It worked fantastically well. So we get state-of-the-art performance. So we get half of the error of LLVM's simulator infrastructure that's sitting in the back end. And we actually beat Intel's own proprietary tools for getting performance models for their chips, what they provide and what you can have access to. And again, it's because even in this situation, there's a very complicated reality that's going on for any given basic block. And it's depending on the events that are being processed in a particular time, right? It's quite detailed. And this is why there's still this gap, even though Intel is putting out these models. On the basic architecture, I'm not to talk too much about that. The architecture of the neural network itself. There are some interesting things that go on there. There's certainly some domain-specific design we did, but it's a neural network. That's all I really have to think about. Right? This was not easy to build just for the data collection, so we actually did have to develop a novel throughput measurement system that actually preserves basic invariants that you have for your performance modeling, such as you have no cache meshes, so everything's at least residing in L1. Things like preemptions, there's a lot of things to handle to actually, a lot of technical challenges you need to solve to even make this a problem to be accessible to machine learning. And those alone were contributions that we had in IceWick this past year. Right, and then finally we tested this. We gathered a lot of data from a wide variety of different programs that are out there, things like Spec, but also other things that we pulled in. And again, Ithemal, I don't want to talk too much about the architecture itself, but the key important part here in this first phase is that this didn't require features. So we were able to actually, this model is actually able to learn its own representations just based on the textual input of a basic block. So oftentimes, you think about these machine learning methods, and what you need to do is you need to take some, let's say, discrete entity, right? We're not sitting in the vision space where everyone says, okay, you can, during vision, an image is just easily mapped as a bunch of continuous numbers, right? And oftentimes in this feature engineering based approach, what you need to do is figure out some set of features. What are the sets of instructions that are in this basic block or something along those lines. So in this case, we're actually not doing that at all. It actually just takes in tokens, maps tokens, it learns mappings of tokens to vectors, individual vectors, and then has a neural network that actually propagates everything throughout. Does particularly well, right? So this, again, not too much detail I really need to go in through here, but again, no features, representations are learned. And the result is that Ithemal, on this example that we have, gets 26.5 as its throughput prediction. Getting right there in the ballpark of Intel's model and what we measure. Right? And so this is great. So what did we do? We took the standard development methodology, that is just the way people build these systems by hand, and we would have called this a program, as we would have called anything else a program, right? That these people are developing, and we've replaced it. We replaced it with the neural network to get better performance, platform independent learning, so we can actually just measure a new data set on, or platform dependent learning, so we can just measure a new data set on a new architecture, a new microarchitecture, get new timings, models ready to go, nothing that we need to change with the model. Whereas in classic approaches, you have to sit there, go back to the Intel manual, or try to refine your prediction by looking where it's mispredicting, look at the Intel manual to figure out where things may have changed, and again, go through this process. So we went from this to this and sort of threw away all this nice structure here. But I wanted to get back to one of these questions, this question that's really out there. And I'd say it's that question that was in the approximate computing community, which is, well, can we do both? Can we combine or compose exact and approximate computation? Right? So what we'd be doing is something like this, but maybe only replacing some subpart of our computation together. Right? And then the question then is, well, what does this computation mean? Right? And so when I say engineering systems that learn, what I want to talk about is, I would say it's really the combination. How do you actually go about combining exact computation with learned computation? Or the component that you're using for this combination is going to be search and optimization. Right? And I think a key feature that you see in many of these spaces is that there are oftentimes approximate specifications for what these components are supposed to do, right? There's no necessarily ground truth that's available. In many of these cases, you're working in this best effort situation. Although this person has crafted a specific program, or the standard methodology has crafted a specific program, you could easily come in and think about integrating these type of techniques to improve performance. So I would say, if you think about this statement, and if you actually think about the related techniques, it brings in a lot of other terminology. And this terminology is used everywhere. So there's this concept of software 2.0 that's been floating around. Differentiable programming, this is a concept as well, where I have these programs and I take gradients against them. Probabilistic programming is something that's there too. Program synthesis, obviously, trying to generate programs for data. Neurosymbolic programs. So I think many of these are in the same wheelhouse, right? Of trying to solve similar problems, or trying to solve similar domain problems. And I'd say they also come up with some of the similar questions exactly about what these computations mean and how we can actually reason about them. Right? So that's it for the systems part. So now I wanted to move on and actually talk about semantics. So when I was talking about approximate computing, I had said that when we started to dive into some of these computations, we started to have these questions. These questions about, well, what actually does this real value computation mean? Or how do we actually think about this probability distribution in a way that we can not only do analysis, but is also faithful to the restrictions that you have in thinking about probability. And so I want to talk about a little bit about some of the work and observations that we've had lately in the past few years. And these two examples I can give you, they are motivated. They're motivated by some computations that we've seen, for example, inside of Ithemal, or just broadly in trying to build deep learning systems. Right? And so the two simple examples I just want to throw up here are these two. Right? So I've got this program on the left, and what it has is takes a floating point value, or it has two floating point values and compares them to be equal. And then the computation on the right, what it does is it's actually an implementation of a ReLU. So this is a standard component inside of your modern neural network architecture, basically used everywhere. Essentially what it does, it takes an input x, right? And if x is greater than 0, it just returns x, and if x is less than 0, it just returns 0. It was an easy one. So what's interesting about these computations, right? So this one on the left, this one should concern you, or perhaps should concern you, right? Where, if you've just even got a little taste of numerical analysis, or worked with someone to do numerical analysis, they would tell you that you're not supposed to do this, right? I think we've all heard this at points where we're not supposed to directly compare two floating point values, right? And the question is always why, right? I'll give this talk, and every time I say this, people say rounding error. This is typically one of the first thing that comes in, rounding error. This is it, and that's not wrong, but the way to really understand this more correctly and more foundationally is to change the specifications of these computations from floating point numbers to actually real numbers. Right? Floating point, essentially, whenever we're writing these computations, we typically have some abstraction. They're usually specified on the reals, right? Some reals. And floating point numbers happen to be a finite precision approximation of the reals that actually lead you to programs that aren't necessarily semantically well posed. Right? So in this one on the left, so this is actually not, right? So this is not a classically computable computation because it is undecidable to actually compare two real numbers. Right? These numbers for infinite precision and in arbitrary points, right, could change in their representation. Right? So this one's not computable. So this is actually the real reason why it actually doesn't make sense to even think about a programming language that has this comparison as admissible, because it's not really well posed. Right? On the right side, so this one is not differentiable, right? So even though all these deep learning systems are driven by taking gradients and computing the derivative of these programs, this one on the right is actually not differentiable at 0, right? And you think about it, because you're coming in, directional derivative, coming from one side is going to be 1, the directional from coming from the other is going to be 0, and this actually does not converge towards the single value that you'd expect, right? So in recent work, we've actually been thinking about these types of problems and giving these things a semantics and trying to figure out, well, what should our programming languages have to say? And so this one on the left, for example, is a case where in some work that we had in LIX a couple years ago, we defined this concept. So this is a little bit of a simplification of what's going on there. There's the concept of approximate or non-deterministic tests and actually having a way in a single programming pattern. So this overlapping pattern match is what we have actually exposed. But a single programming pattern that allows you to look at the full space of considerations for computable implementations of this. So some of them can be non-deterministic, right, for example, or if you have two numbers that are, so basically if two numbers that are very close, you just can't tell. And so you say, I don't know, right? Or you get either or, it's either true or it's false that they're equal. Right? Or in some cases, if you're willing to admit, let's say, partiality inside of your computation, then you can actually say when they're equal, this thing ends up just diverging, the computation diverges. Right? So you can actually now give these reasonable sound semantics that then has implications for how you think about other computations built on top of this. We've actually gone through an ICFP paper we had last year. We use these computable real numbers and the semantics that we put on top of it to actually give novel representations to shapes, so things like 3D shapes that you have in solid modeling, and to actually pose sound algorithms for these types of shapes that are now supported by our programming language. Right? And more recently, we've been actually looking at this one on the right, where, well, what is the derivative? So I wouldn't say there's the derivative necessarily for multiple reasons, but one interpretation of the derivative for this computation on the right is that it's Clark's differentiable. And so what it means is this actually an interval valued derivative. It's that set between 0, the set of 0 to 1, and everything in between. And there are alternative definitions that you might be able to give here, depending on, let's say, the optimization method that you were going to use. But what's interesting is, if you go and look at PyTorch and TensorFlow, they all have implementations of primitives that actually don't have gradient implementations of primitives that don't actually have gradients at some points, right? Sometimes these are measure-zero subsets, and perhaps it doesn't matter. But sometimes there are weird approximations that get stuck in there, and you start to ask these questions. Well, what is this actually supposed to mean? And can we actually drive better solutions based on language and language design? So that's one place. So these are some places that we've been spending some time thinking about the semantics of these computations. All right. So now for the last thing that I actually want to talk about is going to be performance. Right. So I talked a bit about in this space where we have these computations, we're now admitting neural networks, and these neural networks can be large. Right. We'd like to figure out this new area of performance concern that we're now going to have. If we really wanted to deploy this type of performance model in a compiler, we're going to care about compilation times, and we do, and we have to think about how to make these things more efficient and smaller for inference, but also even for training. And so I'll talk about that. So this quick intro: neural networks are large, as I just said. In fact, they are quite massive, right? So this slide is old now, as of at least a few weeks ago. So GPT-2 is one of these large NLP models that's out there. And it has 1.5 billion parameters, right? And more recent models, the more recent effort now has 175 billion parameters. And I think it consumes about 350 gigs of memory. And so this thing is, these are massive. These are quite massive things that are out there, certainly for the state-of-the-art networks that are out there looking at the biggest, most uncertain problems. Right? And so one thing that people have done in practice to try to use these networks, let's say for inference, for actually deployment after you train them, is to do some work in, or apply some techniques called pruning, so neural network pruning. And the idea is that I can take a neural network and find some parts that are superfluous and actually remove them and still get reasonable accuracy out of the resulting model. So now, as background, so this idea goes back to the late 80s, early 90s, almost invariably, as all interesting things deep learning do. And it was revived more recently in 2015 by Song Hong and his collaborators, where they were actually able to show that, yes, you can use these types of pruning techniques on modern models and get very good performance. Right? So to explain what this is, so basic network pruning works like this, at least again for deployment and inference. So the first step is you randomly initialize a neural network. So that's what I have here on this slide. And so you sample random values of the weights, and that's going to be your starting point. You then train that network. So you take data, compute gradients, let that go, right? And until you converge, until you're happy with the accuracy of your network. And then after that, once training has happened, you're going to remove superfluous structure. Right? So you're actually going to now eliminate structure, where structure can mean multiple different things. So channels, filters, so some of these definitions are very attuned to being inside of neural networks, if you know what those are, but other things like weights, specific connections between neurons, or whole neurons themselves, these things can be thrown away. Right? And in the work I'm going to talk about, we look predominantly at individual weights. Now, what makes these things superfluous? Well, there are different definitions. Sometimes it's the magnitude of weight. If it's small and close to zero already, then perhaps you can just set it to zero. That's what eliminate means. I'm just going to set it to zero and forget about it. Right? Or it could be other observations like the gradients falling on the computation is small, right? Or the activations in the large neural network are small. Right? And in the work that we look at, it's typically magnitudes. So now, after you do that, or actually, I mean, just to put this in context, since we're in programming languages and I like to think about code instead of cartoons, right? We can actually take your standard neural network implementation and realize that all this thing really is a matrix vector multiply, at least for the simplest layers. There are more complicated layers that are out there, but this is just code. This is all you've got there. And so you can write this down. And then pruning, what it does is it's a mask, right? So it's actually going to basically mask out some entries of this matrix that you're using, setting these to zero, and that's going to be just fine, right? And that's what it's going to do. Right. And in fact, if you look at the history, or at least the history of how I got into this type of areas, this looks a lot like an approximate computing transformation that we had, where it was loop perforation. And loop perforation, what we did is we took computations and we threw away iterations of loops to see, one, they get better performance, but see how they affected accuracy as well. So we can see this neural network pruning, at least for me, and to some other people, looks a lot like loop perforation. So now, back to this. So remove superfluous structure. You can see what that looks like. And the last step is to fine tune. Right? So what does that mean? What it means is, typically when you remove structure, the accuracy of the network degrades, and then you actually do a little bit more training on a little bit more data, typically not as much, nowhere near as much as what it took to train the network, but that restores and recovers the accuracy. Right? And so these are some results just from Song Hong's original paper, coming back to 2015, and when this again made its reemergence, where you see that this works quite well for a variety of different networks. And what you can end up doing is actually reducing the number of parameters in your model by over an order of magnitude in some cases. Right? So this is great for thinking about this as compression, reducing, let's say, storage costs, but also think about reducing inference costs. So the actual flops required to compute as well. So now this was all for deployment. So I've trained my network, I prune it so that I can deploy it. But we still have this whole expensive training phase. Right. And so training is very expensive, and it's quite expensive. So these are just numbers. If you are really getting into the state of art of training these models, you're going to be spending multi-thousands of dollars a month in cloud credits or machine and capital expenditures just trying to think, trying to get state-of-the-art accuracy for these things. Right. And even, of course, there's relations as well to thinking about just broadly energy consumption and the green qualities of these computations or the lack thereof. Right. And so these latest models are really, really actually getting quite large and prohibitively expensive, taking tens of millions of dollars to run in a single run, for example. So this is sort of the point where we actually started to get in this space, as I've been seeing some of the work in pruning and seeing some of the observations of that, well, if you can prune models after training, we started to ask these questions of, can we prune, or can we actually prune before training? Or can we train smaller models to begin with, right? And so some of the work that we've been doing here has been looking at this type of question, right? Motivation, again, is a pruned network can represent a function that is as accurate as the unpruned network. So why don't we actually try to train the pruned network from the start? Now, if you do this and you follow the results in the literature, what you'll see is that basically you proceed like this, right? So randomly initialize this pruned network. So just a small network, sparse, randomly initialize it as you did your original one, train it to convergence, and what you'll see is that this actually doesn't reach the same accuracy. And this has actually been shown time and time again, right? So when we approached this problem, though, we had slightly different take and made some progress, where, again, our results are essentially that can we train sparsely pruned networks? And it's actually yes. And so our hope, I would say, is somewhat tentatively, is there's this question of, do networks need to be so large to even learn? And there's some hope that this question is no. And so these are some results that we've had in the past year that have had a lot of uptake in the machine learning community, and has actually been developing some very interesting questions, particularly around this later question. What is overparameterization, and how can we actually tackle some of these training costs? All right, so to explain this, just very quickly, the idea is these weights that we find as useless at the end of training were actually useless at the beginning of training. Right? And one key thing here, though, is you need to use the initializations that you had at the very beginning of training, these random initializations. So let's modify this technique. So this is how we went about finding this observation, this experiment that we ran and found to work well, which is first you're going to randomly initialize your full network, as you normally do. You're going to train it. You're going to prune superfluous structure. And then what you're going to do is you're going to backport this structure back to this original randomly initialized network. So it's like taking a subnetwork of this network that you start with. And you can do this repeatedly over time. And what you end up with is, as I mentioned, this subnetwork, some subset of this original randomly initialized network, actually trains just as well as the original network. So we've actually been able to find these for a wide variety of different networks. Using all the different features and various state-of-the-art techniques that people are using inside the machine learning technique community. Now, when you look at true massive scales, so some of these large vision benchmarks, for example, what we find is it's not necessarily at the very beginning of training, but it might be 5% into training. So demonstrating that, well, perhaps 5% into training, you might be able to identify these types of things and dramatically reduce the remaining cost of training. All right. Now, of course, there are some caveats here. Right, I remember just even as specifications, what are the size? So these are about between 1% and 15% of the original size of the network, depending on the network that you're looking at. They learn faster than the original network, and they reach the same or higher test accuracy. Now, again, there are caveats to these networks. We're finding these things retroactively. Of course, we've been making progress of kind of finding these things online, and actually broadly the community has actually been taking up this challenge of, can actually find these things easily at initialization or early training. But the results I'm talking about here are retroactive, just showing the possibility and the existence where people didn't know that this was possible before. All right, finding these subnetworks is very expensive. This iterative process that we're talking about, it's not cheap either. And then as well, so we're talking about wall clock performance. So if you're familiar with any of the concerns in getting high performance for sparse linear algebra systems, then you should know that fewer weights alone does not always equal better performance. Right? Now, we do have results showing that you can get better performance even without doing super clever things, but there's still a lot of room there to figure out how to improve the state of the software and hardware support for this type of sparsity to get what you'd hope to get. And then again, the key observation here is if you reinitialize, so remember this contrast that I said is I just start with a small neural network and randomly initialize it. That doesn't work. The contrast here is doing this backporting, right? So we found inside of this large neural network after training, there was actually something small inside of it that would have worked as well. So now just for some quick results. So here, what I'm showing here is just for a simple model where it's clear to see these types of behaviors, but what I'm plotting here is training accuracy over time. And this is going to be for the original network that we're looking at. So 100% means 100% of the weights remaining. And so this looks like a normal training curve or learning curve, where in the number of iterations, our accuracy goes up and then peaks. And we call that converged. Now, what I'm going to bring in are new lines where we look at the behavior of what happens when you start to look at these small subnetworks that we found. So if we throw away half of the weights and keep 51.3% of the weights, what we can see is we learn a little bit more quickly and reach roughly the same accuracy. If I throw away 21%, or I keep only 21% of the weights, you can see learn a little bit more quickly. And this is again clocked in number of iterations, not necessarily wall clock time, and reach a little bit even better accuracy. But of course, this doesn't go on forever, right? At some point, we start to lose performance, right? But here at 3.6%, or remaining weights, we're actually matching the original network, training just as easily, but now we're definitely an order of magnitude smaller than where we were before. And of course, as I said, it doesn't go on forever. At some point, you don't have enough representation to learn, and things start to fall apart. Right? And so here, just to put that contrast out there, what we can see is I'm going to do the same thing, but I'm going to bring in now another line that shows what happens when you randomly reinitialize. So it's going to be a dashed line. Here's this dashed line. So this is again 51.3% of the weights. And the dashed line is what happens if you reinitialize. And going down, you can see as we make this smaller and smaller, there's actually a growing gap between the quality that you get with our technique versus what happens if you randomly initialize. And here, this presentation doesn't make it as easy to see what's actually happening. And instead, I'm going to switch to this presentation, where what we can see now is an actual is how much difference there actually is between these techniques. So here, what we're showing here is the original initialization, right? So this is going to be, if I look at these slides, so if I look at this graph on the right here, so I've got percentage of remaining weights on the bottom, and my accuracy on the left side. So this is, again, going to be, it's basically looking at that final point in those previous slides, but for a wide variety of different network sizes. Right, so what we're going to see is, of course, as we go down, we go up a little bit, but as we go down too far, we start to lose accuracy. And then on this left side, what we're going to show is actually how long it takes to converge, which is how long it takes to actually match the original accuracy of the network. And so what you can see here is as we make this smaller, we actually get a slight improvement convergence time, but as we get too small, it goes off. Right now, as a comparison, let's look at randomly initialized. So now we actually start to see this gap open up quite substantially, right, where it loses substantial accuracy as well as it does not converge as quickly. And then finally, if we actually rearrange, we start to shuffle these types of mass that we have, we actually see even more performance. So the conclusion from this work is really that we can actually find these sparse trainable subnetworks of these large overparameterized networks. And we can find them using some modifications of some simple techniques. And the real observation here is that we think that these little subnetworks have somehow won this initialization lottery. Right? And in more recent results in the past couple months, we've been pushing on this. Other people are pushing on this, and they've actually been able to demonstrate a variety of different proofs that show that this hypothesis actually has some theoretical grounding in thinking about how this works. So that was it for performance. And so wrapping up, since we're getting to the end of time, the question that I still didn't finish here, right? I talked about an application, several of the problems that we've been looking at. There's still these open questions really of how do you compose exact approximate computation, right? So in some recent results that we've had and we have under submission, we are actually now doing this more specifically in the context of Ithemal, where we are actually implementing this hybrid discrete simulator, or this discrete simulator plus a neural network. And it's been this fantastic exploration in getting these things to work. And as well, what it actually gives us now is an interpretation. And so this is one great thing that we actually see coming out of these results. It's an interpretation of the behavior, the predictions that we're getting from Ithemal, whereas before we actually weren't getting those. We're just getting a precise but inexplicable value. Right? And so this question of interpretation gets to the broader question of systems in this space. So questions around transparency, where we really care about what are the basic properties that these compositions are supposed to satisfy, right? How do we actually go about reasoning something like Jacobi, for example? We rely on this self-stability to actually verify that our computation is going to satisfy these properties. Right? And then finally, what are the modalities for reasoning? Worst case reasoning is typically too coarse. It's something that we found in approximate computing. We oftentimes couldn't put useful bounds on the behavior of these computations. But probabilistic and statistical reasoning are less pessimistic. You can get hopefully better bounds, but there are still open challenges, right? And this very much maps to everything that's going on in the machine learning space. But I'd say it's also, these are strong questions for programming languages people. Of course, I'm speaking to the choir, to many people that are sitting on this call, right? Where you guys are actually looking at techniques for verifying these compositions that have these learned components in it, thinking about robustness, thinking about generalization bounds. How well do these systems generalize to unseen inputs, right? And so to wrap up, I think the landscape of software is actually changing quite a bit. These neural network components, I mean, these are giving us dramatic capabilities to do new things. But even more, this uncertainty is just pervasive. I'm thinking about perception, robotics, so all these applications that are coming out. And it's really pushing, I'd say it's pushing the programming language community to reconsider our emphasis so much on discrete and at most non-deterministic computation. And I think here in this community, we all understand this, and certainly, or in this room, I'd say, in this Zoom room, we understand this. But this, in my opinion, really is just a great future to be in, to think about new problems and to help people build these really new emerging systems. So that's it. That's it for the talk. I know we're over time, but happy to take any questions.
So we have time for questions, and thank you, Mike. It was a very nice talk.
Thank you.
Are there any questions? Now we have a bit of our time, so.
Exactly.
So I have a question.
Yep.
So if I were to, like say I want to train a neural network, and it's super expensive. It seems like the lottery ticket hypothesis just tells me that there exists a neural network, and it's pretty expensive to get to it. So I might as well just train a large network anyways, right? Because of this iterative process, is that right? Or am I?
So that's all the hypothesis tells you.
Right. Yeah.
But in the last few years, we have seen techniques come out that are doing this pruning at initialization. They don't, the results that we're seeing don't match what we're seeing from our results, in the sense that the subnetworks we find have better accuracy than what other people are using, but they are still not so bad, let's say, and they would be better than, let's say, a random dense model of similar size.
Right. Have you also looked at like how the lottery ticket hypothesis generalizes to? I mean, it probably generalizes to these massive text models, GPT-2 and so on. It's probably super expensive to try it out, but is there any indication? And given that like these companies don't care about money, it seems like no one will.
They'd be very interested to reduce their costs, right? When you're talking millions of dollars a run, they do care. It adds up.
Right. So why aren't they doing it? Like,
Well, so I was going to say, so for text, there was a paper out of Facebook that actually looked at this for NLP. And so they're looking at transformer models for translation and showed that, some of this it worked, right? We've done in our Eichler paper this year, we also looked at, again, so these were just more classic RNNs, but again, in translation. We've got a paper in submission where we're looking at BERT models, these large NLP models again. So these are not lottery, it's not true lottery ticket, but it's thinking more about transfer. So we're actually looking, so I don't know if you're familiar with BERT, but it has this pre-training phase, very large, takes a very large model, does a pre-training, unsupervised pre-training, and then does fine-tuning. on specific end tasks that typically have a small amount of data, right? And so in that setting, what we've been able to do is essentially do logic hypothesis in the fine-tuning phase and find these tickets that we can actually transfer, let's say, between tasks. So that's
I see.
what we've done.
I see. Yeah, that's pretty cool.
But still, that still doesn't address that pre-training phase, which is wildly expensive and something that we're working up to.
Right. Right. Cool.
So I have a couple of questions. I might have missed something. If you use the pruning on the fly, is the overall cost less, or does the time go up because you have to search? You have to take the step of figuring out how to do the pruning, or what?
Yeah, so you're right. So the idealized model here would be, I'd say you'd run for some amount of time, let's say with the full model, potentially 0 time. There's going to be some unit of time that's going to take to prune, right? And then there's going to be the remainder of training. Right? So basically the studies that we've done are these, I'd say the limit study. So let's say that you say pruning is free, let's say that. How early in training might it be possible to reduce to a small model? Right? So we're looking at, let's say, that the maximum achievable that we'd be able to find given our current understanding of how to find these techniques. So let's say, right? So now when you take a step back and try to think about, well, how do you operationalize this? This is something that we're working on right now. This summer, you now do need to think about, well, what's the cost of pruning? So some of these techniques that are out there that are trying to do this early pruning or pruning at initialization, they're not that expensive actually. They take maybe a mini batch of data, a couple of mini batches of data, compute some gradients and do something. So it's nothing to really think about. And so then the real question is, how early in training can you do this? And like I said, these tend to come in somewhere about 5 to 10% in training, right? So then the last part is, how small can you make the model to accelerate that last bit of training, right? So that you can get improvements. So
can you learn the mask as you go along? I mean, can you make that part of the learning algorithm?
Yeah, so there was an Uber paper this past year, or a paper out of Uber Labs, that did look at this. They tried to dynamically learn masks on the fly, and they showed that it's possible. You can make some progress, right? But none of these techniques so far have matched, let's say, the limit that we're finding. And so so there are other techniques as well, where you think about this as L0 regularization, if this is a meaningful term to you. But there are other techniques that put this more into a regularization framework, a classic machine learning regularization framework, where I want to learn a sparse representation at the end of training. And then so the question is going to be, well, how sparse is that throughout training if you're thinking about performance? Because some of those techniques don't really care about getting sparsity until the very end of training. And the reason why they might care about sparsity is oftentimes sparsity is correlated with improved generalization. This is something that happens. That's why you think about regularization. And also people think about sparsity for interpretability. If there are fewer weights or fewer features you need to deal with, and hopefully you can interpret the predictions better, right? So I'd say that's a related field. And they're really thinking about very similar problems there, right? And so there are opportunities. And so this summer, we're trying to put out one of the first papers there that tries to put all these techniques on a specific axis, compares them all, and comes up with good metrics. Because as does happen, I guess, in the course of research, and certainly in the course of machine learning research, there are a lot of things that have just been put out. Right? That's what I'd say. So I'd say, yeah, there are opportunities, but the space isn't well organized yet.
And have you thought about using distillation instead of pruning?
Yeah, distillation could work in this space as well. That'd be another thing. So my basic understanding for distillation, and maybe you've had different results, but with students I've had work with it is, so the problem with distillation is, I've got this model, and now I need to get this other model. It's going to mimic the behavior of the other model. And there's this whole question of hyperparameter settings, model architecture, everything, right? So the pruning techniques that we've looked at, they use the same hyperparameters as whatever you used for your original model. Right? So I would argue that it's a simpler method to control, since I've certainly seen some of my students get lost in that space, and just heard widely that people have issues with distillation.
Yeah, we tried something a bit like that here, and and didn't get good results.
Yeah, that's. I think it's hard. Right? I mean, it's this student teacher model. It makes a lot of sense, but it seems like the results don't quite pan out.
Oh, I had another question about this Clark differentiation.
Yes.
So were you dealing with a step function? Is that what it was?
Yeah. So it's so not step functions, but it's basically, it looks like this. So it is flat. It's 0. So below 0, it's just all 0, and then it comes up, right? And then it's just linear above 0. So right there, you have a hinge, right? So at the hinge at 0.
Yeah. Okay.
You can have a problem. Yeah, I should put in. I need to put a figure on that slide.
But so with a step function, it would go to infinity, right?
So in the step function, I'm trying to think. I think there you actually do just end up with nothing useful. It's going to end up being just 0 everywhere, I think, in the classic presentation. Okay.
Okay, I think we are a good time over, so we should probably wrap it up. But it was very nice talk, and thank Mike for joining our seminar this week. And of course, you're welcome to join the future ones.
Sure, thank you.
Thanks a lot, Mike. Thanks a lot.
Yep, thank you.
All right, thanks.
Yeah, thanks. Bye.
Take care.
Have a good week.
Yep, have a good one.